Let us start with lecture number 33 of this course. Now today I am going to discuss the principle of another popular neural network, that is called counter propagation neural network. In short, that is known as CPNN. CPNN. Okay. Now the concept of CPNN was proposed in the year 1987. Okay. Now this CPNN consists of three layers. As usual, there will be input layer. Then we have got unsupervised coherent layer as the middle layer. And we have got one output layer, and that particular output is a teachable output layer. And this layer will perform some sort of supervised learning, that is Grossberg learning. Okay. So on the hidden layer, we have got the unsupervised coherent layer, and output layer is nothing but uh, the Grossberg learning layer, which is nothing but the supervised learning layer. So this particular network uses the concept of both unsupervised as well as the supervised learning. Now remember, this is the only network which uses the concept of both unsupervised as well as supervised learning. Okay. Now let us try to understand the working principle of this particular network, that is counter propagation neural network. You have studied back propagation neural network, that is nothing but the multi-layered feed forward network trained using back propagation algorithm. You have studied recurrent network, which is having both feedback and feed forward circuit. Okay. And this is the counter propagation neural network is another type. Now, if you see its construction wise, it consists of one in star model and one out star model. Okay. Now, what do you mean by the in star model? In star model is formed by the input and the coherent layers, that is the middle layer. Okay. And the out star model is formed using the coherent and the output layer. So I'm just going to discuss in details like the principle of in star and out star models used in CPNN. Now, if you compare the performance of this particular CPNN with that of multi-layered feed-forward network trained using back propagation neural network, that is popularly known as BPNN. So this CPNN is found to be computationally faster compared to the BPNN. Okay. And in terms of your accuracy, if you compare, then CPNN could be somewhat inferior compared to your BPNN. So in terms of accuracy, BPNN could be more accurate compared to your CPNN, but CPNN is faster compared to your BPNN. Okay. Now this CPNN, that is the counter propagation neural network, could be of two types. It could be either full CPNN or a forward only CPNN. Now I'm just going to discuss the principle of full CPNN and forward only CPNN. Now let me first concentrate on the full CPNN model. Okay. Now the full CPNN model consists of two input layers, two output layers with a common hidden layer to them. Okay. Now let us concentrate on the architecture of full CPNN. Now supposing that I've got a process and that process has to be modeled. Its input output relationship are to be modeled. Okay. Now supposing that we have got small m number of inputs for the process and your small n number of outputs of the process. Okay, I'm sorry because this particular the figure has been made very smaller. Okay, small one. It may not be easily readable, but please bear with the situation. So on the input layers, there are two input layers. One is the first input layer to represent the input process parameters, and the second input layer represent the output or the responses of your the inputs. Okay, so this is the first input layer and the second input layer. There are two such input layers. So the first input layer contains information of the process parameters, and the second input layer is going to carry information of its corresponding responses. Say there are small m number of inputs and small n number of outputs. So I think I'm clear to all of you. And this is the output layer. On the output layer, once again, there will be two output layers. One is actually the output layer corresponding to the process parameters, and another is nothing but the output layer representing the responses corresponding to the input process parameters. Okay. Now here you can see I have represented the output layer by star. So x1, x2 up to xm star represents the approximated x star outputs, and y1 star, y2 star up to yn star represent the approximated y star outputs. Now let me repeat, there are two input layers, there are two output layers, and here in between the input layers and the output layers, we have got one hidden layer. Okay. Now, this particular input layer and hidden layer is going to constitute what do you mean by the in-star model, and this hidden layer and the output layer is going to form the out-star model. Okay. Now, how to carry out the calculation in the in-star model and the out-star model, that I'm going to discuss in details. Okay. Now, let me first concentrate on the training of the in-star model. Now, if you remember, what is there in the in-star model? In-star model is nothing but the two input layers and one hidden layer. Okay. Now, here you can see the two input layers x1, x2, xi, xm. Okay, this is one input layer, and the second input layer is going to carry information of y, that is y1, yk, yn. Those are nothing but the corresponding responses. Okay, and in between we have got like the inputs are coming both for the x input and y input to the hidden layer. You can see the direction of arrows here. Okay, and this hidden layer consists of how many neurons? Small p number of neurons. That is Z1, Z2, Zj up to Zp. The connecting weights between the X input layer and the hidden layer are represented by U matrix, and the connecting weights between the Y input layer and the hidden layer, those are represented by the V matrix. Okay. Now let us see how does it work. So I'm just going to discuss how does it work. Okay. Now we generate the connecting weight U and V at random, lying in the range of 0 to 1. Okay. So if we just concentrate on the connecting weights, that is U and V. So U is the connecting weight between the X input layer and the hidden layer, and V is the connecting weight between Y input layer and hidden layer. And initially U and V values are generated at random using the random number generator, and these values will lie between 0 and 1. Okay. Now we are going to use some learning rate. So alpha is the learning rate lying between 0 and 1 between the X input layer and hidden layer, and beta is the learning rate between Y input layer and hidden layer. Okay, and here we are going to use Cohen self-organizing map. Okay, during the training of instar model. Okay, so I have already discussed in detail Cohen's self-organizing map, which is some sort of unsupervised learning. Okay, now here in this particular CPNN, we are going to use Cohen's network, that is unsupervised learning based on the competitive learning. Okay, in the instar model. How to implement that I'm going to discuss. Now to implement the coherence learning in the instar model, so what I do is we try to calculate once again the Euclidean distance. Now the Euclidean distance is what? That is the Euclidean distance between the hidden neuron and the connecting weights. Okay. And we also consider the inputs and the outputs. Okay. So we try to find out the distance between the input and its corresponding connecting weight. Okay, the difference between the output and its corresponding connecting weight. If you see this particular expression, you will understand. Now dj, j varies from 1 to up to p. P, what is p? P is the total number of neurons lying on the hidden layer. Now out of these p neurons, I'll have to find out which one is the winner. And how to decide the winner? The hidden neuron which is having the the minimum value of Euclidean distance, that is d, will be declared as the winner. The way we did while discussing the self-organizing map, if you remember. Okay. Now this dj is nothing but square root summation I equals to 1 to m xi minus uij square plus summation k equals to 1 to n yk minus vkj square. J varies from 1 to up to p. Okay. And this uij updated is nothing but uij previous plus alpha multiplied by xi minus uij previous. And alpha is nothing but the learning rate between the X input and the hidden neuron that I have already mentioned. And here I varies from 1 to up to M. What is M? M is the total number of input process parameters. Okay. Now how to update this VKJ? That is the connecting weight between the Y input values and its corresponding your the connecting weight. Now this VKJ updated is nothing but VKJ previous plus beta into YK minus VKJ previous. What is beta? Beta is nothing but the learning rate between the Y input and its corresponding connecting weight. Okay. So K varies from 1 to up to small n. What is small n? Small n is nothing but the total number of responses. Okay. And once you have got, so these particular d values, now we can compare. Now, how many d values we are going to get? It is very simple. We are going to get small p number of d values. Now we compare and find out which one is the minimum. Now the hidden neuron corresponding to the minimum number of Euclidean distance is declared as the winner. Okay, and that completes actually your instar modeling. So at the end of the instar modeling, I'll be getting one winner neuron. Okay, and once you've got this particular winner neuron, now we are going to use the property of the winner neuron to train this particular network further. Okay, how to do it, that I'm going to discuss. So I'm just going to discuss the principle of this outstar training. Now, as I told, we try to find out the winner hidden neuron. Supposing that jth neuron is found to be the winner hidden neuron, and that is denoted by ZJ. Okay, now from this ZJ, now you can see the direction of the arrow. We are moving towards X star values, and we are also moving towards Y star values. What is X star values? X star values are related to the outputs. Okay, X star outputs, and Y star values are related to your Y values. That is the responses. Okay, and the connecting weight between the winner hidden neuron and your X star output layer, so that is denoted by W matrix, and the connecting weight between ZJ winner hidden neuron and your Y star output layer, that is denoted by your S matrix. Okay, and we'll have to update both this W and S matrices also. Okay, and for updating, we are going to use some sort of supervised learning, that is called the Grossberg learning. Okay, so exactly the same thing, whatever I discussed, I have written it here. The connecting weight W and S are generated initially at random, lying in the range of 0 to 1. And we have got the learning rate like your gamma. Gamma is the learning rate between the winner neuron ZJ and X star output layer, and delta is the learning rate between ZJ and Y star output layer. Okay, now how to implement that I'm going to discuss here. Okay, so I'm just going to discuss how to use the Grossberg learning on the outstar model of these particular the CPNN. Now the updated weight, that is WJI updated, is nothing but WJI previous plus gamma into Xi minus WJI previous. Now here I varies from 1 to up to small m. Then SJK updated is nothing but SJK previous plus delta into YK minus SJK previous, and K varies from 1 to up to N. That is the total number of responses. Okay. Now this process of updating will be going on. Okay. And ultimately we'll be getting Xi star is nothing but WJI updated, and YK star is nothing but SJK updated, and it completes one iteration of your outstar training. So I have discussed the principle of both in-start training and the out-start training. Let me repeat. During the in-start training, we use some sort of unsupervised learning, that is the coherent learning. Okay. And in the out-start training, we use the principle of some sort of supervised learning, that is called the Grossberg learning. And by combining both the supervised and unsupervised learning, we are in a the solution for indicating the input output relationship for any such engineering process. Okay. Now this is the principle of your full CPNN, full counter propagation neural network. Solving one numerical example soon. Okay. Now, before I solve this numerical example, let me concentrate on the principle of forward only CPNN. Now, remember one thing, this forward only CPNN consists of only one input layer, one output layer, and a common hidden layer between these two input and output layer. Let me try to find out the difference. A full CPNN consists of two input layers, two output layers, and one hidden layer in between. On the other hand, the forward only CPNN consists of one input layer, only one output layer, and a hidden layer in between the input and output layers. Okay, so this forward only CPNN is much simpler compared to your full other CPNN. Okay. Now, exactly in the same way, you'll have to go for in-star model and the out-star model. And in the in-star model, the way I discussed, you'll have to use the coherence learning. And in the out-star model, once you've got the winner hidden neuron, okay, you can implement the out-star model using the Grossberg learning. Exactly in the same way, we can implement your out-star model, in-star model and out-star model. Okay. Now I'm going to solve one numerical example. Just to make it clear, I have designed a very simple numerical example. Now let us assume a full CPNN, and this full CPNN is to be used to represent the input-output relationship of a particular the process. And supposing that we have got three inputs x1, x2, x3. So these are the inputs, that is the input process parameters x1, x2 and x3, and those are kept equal to 0.3, 0.5 and 0.6. And we have got two responses y1 and y2. Y1 is kept equal to 0.3 and y2 is kept equal to 0.4. Okay, and let us consider only two hidden neurons for simplicity, that is your Z1 and Z2. And we have got the two output layers. So this is the in-star model and that is the out-star model. Now let us try to calculate in the in-star model. Now supposing that the initial weights, that is U, V, W and S, those are generated at random using the random number generator. And as I told, this individual connecting weight value will lie in the range of 0 to 1. Okay. So these are the U values, U11, U12, U21, U22, U31, U33, 32. You can see these numerical values generated at random, the V value generated at random, W value and S values. Now let us see with these values, how can I proceed with the calculations? Okay. And let me assume the learning rate values are as follows. Alpha, that is 0.2, that is the learning rate between the X input and the hidden layer. Beta is the Y input and hidden layer. Gamma is actually X output and the hidden layer. And delta is nothing but the hidden layer and Y output layer. Okay. And all such values are lying in the range of 0 to 1. Calculate the values of x1 star, x2 star, x3 star and their corresponding y1 star and y2 star at the end of first iteration. So let's see how to carry out this particular the calculation. It is very simple. So once again, I'm considering the in-star model. You can see that these are the x inputs, these are your y inputs, and this is nothing but the hidden layer consisting of two neurons Z1 and Z2. And I have written all such connecting weight values here, which are selected at random using the random number generator. And these connecting weights are also selected at random using the random number generator. Okay. Now, as I told several times, that in-star model uses the principle of coherent learning, that is nothing but unsupervised competitive learning. And how to implement that? We calculate the Euclidean distance. Now here, there are only two neurons on the hidden layer. So I'm going to calculate only two D values, D1 and D2. Okay. How to calculate D1? Very simple. Square root summation I equals to 1 to 3 xi minus ui1 square plus summation k equals to 1 to 2 yk minus vk1 square. And if you substitute all the numerical values, you'll be getting 0.51 as D1. Okay. Now what we do is we calculate D2. Now D2 is nothing but uh, square root of summation I equals to 1 to 3 xi minus ui2 square plus summation k equals to 1 to 2 yk minus vk2 square. Substitute the numerical values, you will be getting d2 equals to 0.44. Now, how much was d1? d1, if you remember, that was 0.51 and d2 is found to be equal to 0.44. That means your d2 is less than d1 and consequently Z2 will be declared as the winner. And that completes your INSTAR model training. Okay. And once you've got this particular winner, now we can concentrate on your the outstar model. But before that, we can update your the connecting weights, that is u1 to updated is nothing but u1 to previous plus alpha into x1 minus u1 to previous. You substitute the numerical values, you will be getting the updated value of u12 and that becomes equal to 0.3. Similarly, U22 updated is nothing but U22 previous plus alpha into x2 minus U22 previous. You substitute the numerical values, you will be getting 0.58. Then U32 updated is nothing but U32 previous plus alpha into x3 minus U32 previous. Substitute the numerical values, this will become equal to 0.52. Similarly, we can also find out the updated values for this V12 and V22. Okay. And once you've got the updated values, now we can concentrate on the outstar model. Now we have already seen that we have got only one your winner neuron, hidden neuron, that is nothing but Z2. Okay, and from this winner hidden neuron, I'll be getting connection to X star, I'll be getting connection to Y star, and these are all initial values of the connecting weights generated at random using the random number generator. Okay, now we'll have to update using the Grossberg learning. Okay, now W21 updated. What is W21? W21 is nothing but, so this is W and this is S. W21 is this particular connecting weight. W22 is this. W23 is this. S21 and this is your S22. Okay, and we are trying to find out your the updated value of W21. W21 updated is nothing but W21 previous plus gamma into X1 minus W21 previous. Substitute the numerical values, you'll be getting 0.21. Similarly, I can find out W22 updated, W23 updated, S21 updated, okay, and then comes your H22 updated. And once you've got all such updated connecting weights, now we can take the decision that if x1 star is 0.21, x2 star is 0.32. Okay, how do you get 0.21? This is your this 0.21 updated value for this W21. Similarly, updated value for W22 is 0.32. Updated value of W23 is nothing but 0.42. You can see that X1 star is 0.21, X2 star is 0.32, X3 star is 0.42, and its corresponding responses, that is the outputs, are nothing but Y1 star. Now this Y1 star is nothing but your S21 updated, that is 0.42. So it is 0.42 and Y2 star, that is nothing but 0.58. Okay, so this is the way, in fact, you can find out the input output relationship of this particular process using the principle of counter propagation neural network. But as I told, in terms of accuracy, it may not be able to defeat the accuracy of BPNN. But in terms of computational complexity, CPNN is faster compared to your BPNN. Okay. In fact, we implemented to model some manufacturing processes a few years ago, and we could get very good results using CPNN also. Okay. So this is the working principle of CPNN, and I hope you got the idea like how to use the CPNN, that is the counter propagation neural network, to model the input output relationship. Now to summarize, while discussing the neural network, we used the multi-layered feed-forward network trained using both backpropagation algorithm as well as genetic algorithm. Then we concentrated on your radial basis function network. We discussed the principle of your recurrent neural network and this counter propagation neural network, which uses the self-organizing map also. Okay, so using this network, we can establish the input-output relationship of the process. Okay, so I hope I'm clear. And the purpose of this particular course was how to design and develop the knowledge base, or how to design and develop the knowledge base of a system which can predict online the input output relationship of a very complicated process which could not be modeled mathematically easily because physics is not known 100%. So I hope I'm able to give you at least some initial momentum in this particular field so that you can think further in future. And if you are willing, you can concentrate for your future career. So in this particular, the research areas. Okay. So I hope I'm clear to all of you. But if you have any doubt, you can ask me now.
Sir,
Yes.
sir, here input variables x1 and y1 are taken as constant values for a problem, but the weighted parameters are taken as a random. So the updated weights are taken as a output. Updated weights are taken as a output. So this will give a good result or
In fact, this may not give, as I have already mentioned, that in terms of accuracy, there could be some problem. Okay, it cannot be as accurate as your backpropagation neural network. Okay, in backpropagation neural network, if you remember, we use the gradient-based optimization tool. Okay, that particular gradient-based optimization tool is not used here, but it is a very simple method. That is why its computational complexity is much less. And it has got one advantage. The solution may get trapped into the local minima. Are you getting my point? So that is one advantage over your the back propagation neural network. But computationally, it is much faster. But in terms of accuracy, it may not be as good as your BPNN. This may give rise to some approximate input-output relationship. Okay, but at the cost of low computation, less computation. It is
sir, in this
computationally much
problem,
faster.
sir, in this problem, the input variable or input variable are taken from 0 to 1, and also weighted parameters are taken from 0 to 1. But if in this problem, suppose the inputs all input variables suppose greater than 1,
Huh.
then
In that
how?
case, the way I told for this multi-layered feed-forward network, if the inputs are not lying within the normalized scale, you'll have to convert it to the normalized scale. Okay,
Okay, sir.
that was not the case with fuzzy reasoning tool. fuzzy reasoning tool, you can pass the real values. You need not pass within the normalized range. If you remember, fuzzy reasoning tool.
Yes.
Okay, but for the neural network, almost in all the neural network, we pass the inputs into their normalized scale. Okay, the reason I've already told. So here also, if the inputs are having some other real range, you'll have to convert to the normalized range. Okay, and after getting the results, after getting the output, you'll have to denormalize to find out what could be the real values for the output. Same is true for multi-layered feed forward network. So in the input layer, before we pass through the input layer, we do normalization. Are you getting my point?
Yes, sir.
So we are getting the output on the output layer, but that particular output could be in the normalized scale. So once again, I'll have to denormalize to go to the real scale. Okay, the way we normalize, exactly using the same information, you'll have to denormalize.
Yes.
Okay, that is true for all the networks.
Thank you, sir.
So is there any other doubt? Now, if there is no
Excuse me,
other
sir.
doubt, please.
Sir, I don't have a doubt. I just have a query regarding the exam. Sir, can the exam be scheduled away from Friday? Because
No,
we have. Thank you, sir.
absolutely no, absolutely no. Please cooperate with me because see, I have number of other activities. Okay, and once I have scheduled, if I want to change it, I'll be in deep trouble. Don't think that this is the only responsibility which I'm having at least 12 responsibilities at the same time. Okay, or even more. Be careful about that. Okay. So I'll request all of you
Thank
to
you,
sit for the exam as we scheduled. Okay. The exam will be held on 13 at 9 a.m. Very simple exam. Okay. And it will be MCQ. There will be 10 questions. Okay. As usual, the same pattern. Okay. But another thing that is your regarding the assignment. So till now, I have given 4 assignments. I think all of you have submitted all 4 assignments. Okay. Now I'll have to give the last assignment, that is your assignment 5. Okay. And I want to tell something regarding the assignment 5. Okay. Now this assignment 5, there will be no numerical example. Okay, so till now, all the 4 assignments and 3 tests, I gave some sort of numerical example or a very crisp questions. Are you getting my point? Now your assignment 5, there will be one problem. Problem in the sense, not the numerical example. Okay, but that particular problem, there will be enough fuzziness. That requires the thinking, lot of thinking, whatever you have learned throughout the course. Okay, so I'm just going to find out whether you people have understood the content of this particular course well or not. Okay, and accordingly, I'll be giving you assignment 5. Okay, so assignment 5, you'll have to write something. Okay, using some might be only 10 sentences, not more than 10 sentences. Okay. There will be 10 points and each point will carry one sentence. Don't use 2 sentences or more than 2 just to indicate a particular point. Okay, so one point will consist of only one sentence, and accordingly I'll be designing one problem for assignment 5. Okay, and today in the evening I'm just going to send you that assignment 5, but I'll give you the due date will be, so 13th is exam. Okay, and due date will be I can give you up to 15th, say morning up to 12. 15th is on the Sunday. Okay, and I can give you one guarantee that if you have understood this particular course, solving that particular assignment will take only 10 minutes time. Okay, and those who have not studied, those who have not understood, they may take 10 days time to answer that particular assignment. Okay, but I cannot wait for 10 days. So the due date for this assignment 5 will be your 15th, that is Sunday, 12 p.m., 12 noon. Okay, and as I told, let me repeat, if you have understood the course, it will take only 10 minutes time for you to give reply to assignment 5. Okay. Acha, another thing I'm just going to tell you, and purpose also I'm going to tell you. I'm very frank in this. Okay. Now, this assignment 5 may have slightly higher weightage compared to your other assignments. So please do not miss assignment 5. Okay. And while checking assignment 5, so I'm going to consider not only the correctness of your answer, but also the similarity of your answer. Supposing that out of say 53 or 54 students of this particular course, knowledge-based systems in engineering, supposing that I'm getting like 40 answers are similar, all 40 will be put one fuzzy cluster and they will be getting less marks. Okay, so I'm going to give more weightage on the outliers if the answer is found to be correct, and if it is outlier, that means he or she did not share the answer with others, and neither he copied or she copied from others, definitely that student should get the highest weightage in this particular assignment. And this will help me, purpose also I'll tell you, this will help me to decide your grades correctly. Okay. And I think some of you might be knowing I'm professor in charge examination for the whole institute. Okay. And during our UGPC and PGPC meeting, I also gave the same opinion. Okay. Whatever I mentioned to the whole institute, all the faculty members, they should also follow this particular principle. Okay. Just to find out the difference of their performance of the student, at least one assignment should be of this type. So this suggestion I have given to all the faculty members of our institute in the last UGPC and PGPC meeting as PIC, that is the professor in charge of examination for the whole institute. I do not know whether others are going to follow or not, but I told I am going to follow. And if I can follow it meticulously, the problem of grading could be solved very efficiently. I hope you understood the practical meaning of this particular assignment. Okay, so please cooperate. I do not know whether you enjoyed the course, but as a teacher, I enjoyed this particular course a lot. Okay, and thank you very much for your all cooperation. I hope you at least got some idea of this particular the course. And as I told, the fields are very wide. Okay, if a student wants to continue for his or her whole career on any one of these particular fields, he or she can do that. It's such a vast. Okay, but I tried my level best to give you the initial momentum. If you remember, while discussing the particle swarm optimization, okay, I mentioned that I gave you W multiplied by your what? V. Okay, that is the initial momentum, but your cognitive component and the social component you'll have to design if you want to do or carry out optimization just like your the particle swarm optimization. Okay, So with this, let me stop here today. I
Sir,
wish you all the best. Yes.
sir, what will be the syllabus of test 3 up to
Test 3 syllabus will be whatever I covered after test 2 up to today's class. Okay.
and sir
That
tomorrow's class?
tomorrow's class I'll be coming at 11. Okay. If you have any doubt, that will be the last chance to ask me. Okay. So there will be doubt clearing. And moreover, I think for one student, I'll have to take one repeat test because I think he or she missed the first test. Can I know the name?
Yes, sir, I missed the test.
Okay. So for you, there will be a viva related to your test 1. That means your optimization.
Okay,
Okay.
sir.
So first, there will be doubt clearing session. After the doubt clearing session is over, then I'll be taking the viva just to compensate your test 1. Okay. And please do not miss test 3. I'll not be able to take any compensation test. Okay. And also do not miss assignment 5. And the purpose of assignment 5, I've already told you. Okay. So all of you please submit assignment 5. Most probably today in the evening, I may send you the assignment 5, okay, through your ERP mail. Okay. Okay.
Okay,
So
sir.
with this,
Thank you.
thank you.
Thank
With
you,
this,
sir.
thank you very much. With this, let me stop today's class, and tomorrow we are going to meet for the doubt clearing session. So if you have any doubt, so note it down and please ask me tomorrow in the class, and we are going to start tomorrow at 11. Okay. Okay. Let me stop here today.